ZK-Rollups are powerful, but they still involve practical engineering trade-offs. As we move from concept to evaluation, we'll look at proof costs, compatibility, decentralization, bridges, upgrades, and the operational risks teams need to manage. So far, we've covered why scaling is needed, how Ethereum can act as settlement, and how ZK rollups prove and publish transactions. Now we turn to adoption. What costs, constraints, and risks still matter before we move into privacy? A ZK rollup does not simply make scaling problems disappear. It reduces Ethereum's execution load by moving work off-chain, then anchors results back to layer 1 with proofs. That shift creates new design choices. Proving systems cost money. Operators add complexity. Bridges, governance, data availability, and code quality all affect security. So when comparing rollups, look beyond transactions per second. Ask what trade-offs the system makes and who users still need to trust. Validity proofs are expensive because the rollup must translate transaction execution into algebraic constraints, then prove those constraints were satisfied. Basic transfers are relatively manageable, but smart contracts, NFTs, and DeFi interactions produce much larger execution traces. That workload can push provers toward GPUs, FPGAs, cloud clusters, or distributed proving networks. In practice, proving is not just a cryptographic step. It affects user fees, confirmation latency, infrastructure cost, and whether the rollup's economics can scale. The main driver is how much computation the prover must faithfully check. A token transfer has fewer moving parts than a DeFi trade involving multiple contracts and state changes. EVM equivalence gives developers flexibility, but it can be harder to prove than a VM designed specifically for proofs. Batching helps spread fixed costs across more transactions, though users may wait longer. And these costs are not fixed forever. Better circuits, GPUs, parallelization, and algorithms can steadily bring them down. Think of batching like shipping packages. A full truck is cheaper per package, but you may wait for the truck to fill and for the proof to be generated. A smaller delivery leaves sooner, giving users faster responses, but each transaction carries more cost. Also, confirmed can mean different stages: accepted by the rollup, proven by the ZK system, and finally settled on Ethereum. EVM compatibility creates a balance between developer convenience and proving efficiency. When a rollup feels like Ethereum, teams can reuse Solidity contracts, wallets, libraries, audits, and familiar workflows. That lowers adoption friction. But the EVM was not designed for zero-knowledge proofs, so full compatibility can make proving harder. More custom environments can improve performance, but developers may need to adapt or rebuild their applications. Not every ZK rollup follows the same design. A ZK EVM keeps Ethereum compatibility front and center, so existing contracts, wallets, and tooling work with less friction. An app-specific rollup narrows the scope, optimizing around one job such as trading, payments, or gaming. A custom VM goes deeper by changing the execution environment to make proving faster or more flexible. The key tension is compatibility versus specialization. Broader access usually leaves less room for performance tuning. Compatibility also shapes the builder experience. It affects who can build, how quickly they can ship, and what risks they inherit. EVM-compatible rollups make Solidity apps easier to migrate, while the proving system may be more complex underneath. Custom environments can unlock performance, but developers face new languages, tools, and audits. A strong choice balances user experience with developer readiness. Wallets, RPCs, explorers, debuggers, documentation, and integrations. Many rollups today gain speed through a practical shortcut. One main sequencer orders transactions and gives users fast confirmations. This works well for performance, but it concentrates power. If the sequencer refuses a transaction, goes offline, or chooses an unfair order, users feel the impact immediately, even though Ethereum still protects final settlement. That is why sequencer centralization is usually treated as a temporary phase. Ethereum secures the rollup's end state, but sequencing shapes everyday fairness and usability. Decentralizing sequencing is a spectrum, not a single design. A shared sequencer can serve several rollups with one neutral ordering layer. Permissionless sequencers open participation, allowing operators to compete or rotate. Validator committees use selected groups with accountability. Each path reduces single operator risk and improves censorship resistance, but introduces coordination, incentive design, latency, and governance challenges. The goal is credible neutrality without losing the speed users expect. Even with strong proof security, users still rely on the bridge to move value in and out. Deposits are locked on Ethereum, then credited on L2. Withdrawals reverse that flow through messages, proof checks, and release logic. A bug in those contracts can threaten the pooled assets they custody. That is why bridge design, audits, monitoring, and conservative upgrades are central to real-world trust and institutional adoption. Upgradability is not automatically a weakness. For young ZK-Rollups, it can allow teams to fix bugs, improve proving systems, and respond to emergencies. The risk is who controls that power. Admin keys, multisigs, voting rules, time locks, audits, and pause functions all define the real trust model. Before relying on a rollup, ask whether it is immutable today, still upgradable, or moving toward decentralization, and how visible each change is to users. Choosing a ZK rollup means choosing an operating environment, not just faster settlement or lower fees. A lending app, for example, needs to know whether RPCs stay reliable under stress, provers and sequencers recover quickly, and monitoring is mature. It also needs wallets, oracles, liquidity, explorers, and indexers ready on day one. Then come audits, bridge risk, governance controls, and incident response. The best rollup is the one whose trade-offs match the product's risk, latency, and composability needs. ZK rollups offer major benefits, but they come with trade-offs. They shift costs into proving, latency, and infrastructure. Compatibility shapes what developers can build. Decentralization depends on sequencers, bridges, upgrades, and governance. With that practical lens in place, we're ready to examine privacy and why public blockchains need better protection for sensitive data.